messy, but also a little adorable.
That's a word for it.
Well, if you love dogs, I mean, if you don't love dogs, why have a dog?
Right.
Right.
I mean,
I mean, they don't understand, you know, they're not doing it to be a nuisance.
yeah. One of my dogs, she used to do that. She doesn't anymore because we put trash in the bowl.
It's called removing temptation or something, I guess. I don't know. My office upstairs is not very well heated either.
Oh, you have your office back?
No, but I'm sort of camping out. That is,
God.
I take all my stuff that I need to teach home every day, and then I bring it back every day, and I, you know, whatever. It's, why don't they just, I don't know, it's okay.
Have they started fixing it?
They have, no,
Well,
not at all.
Sucks.
It's, but, you know, I mean, I don't know, I mean, maybe they have higher priorities and maybe that's legitimate and so on. Okay, it's 3:30, so let's get started. We'll wait no longer for our compatriot. And, where we stopped, I'm informed, was in the middle of a chapter of problem number 7. And I kind of did this on purpose to stop there, because A, I didn't have time to finish, of course, but also B, because we hadn't yet gone through sections 6 and 7. And it's section 7 that this problem, that the latter half of this problem is on. So let me just briefly go through section 6 and section 7. Section 6 is the large N limit. And you will remember from quantum 1 that we have this very important principle we call the correspondence principle. And what that says is that in the limit that the system goes over to the classical realm, classical mechanics must obtain. That is the classical limit of quantum mechanics, in order for quantum mechanics to be correct, had better be classical mechanics. Or we've done something wrong, because we know that classical mechanics is correct. And in section 6, which is a very short section, he just discusses this large N limit. Okay, so there are several different ways we can take the limit as a quantum system becomes classical. One limit you're familiar with is h bar goes to 0, so classical limit. Can she spell limit? Okay, so h bar goes to 0 is one way of talking about the classical limit. Now, this often disturbs people when I say h bar goes to 0, because h bar is, after all, constant. And how can it become 0? Well, just to reiterate something I'm pretty sure we said in quantum 1, it doesn't actually equal 0, but you notice that h bar has units. Okay? Now, it doesn't make any sense to say that pi goes to 0, because it has no units. Okay? But h bar goes to 0 does make sense in the sense that the units of h bar are the units of classical action. In other words, position times momentum, obviously, or energy times time, also obviously. The units are usually expressed as joule seconds, or yeah, well, whatever. And when we say that h bar goes to 0, what we really mean is that the things in the quantum system that have the same units as h bar, like delta x times delta p, which has the same units as h bar, are very, very, very large compared with h bar. So one way of saying this is the classical limit is saying that h bar divided by delta x delta p goes to 0. Okay? In other words, h bar is small compared to the product delta x delta p. So what we really mean by this is something like this, something that has the same units. Okay, Well, there are other ways of saying what the classical limit is. And in particular with the harmonic oscillator, in this section, he discusses the large N limit. So this is one way of doing it. Okay, here's another way. And we'll see other ways in the course of the course. Ooh, that didn't come out very well. Energy becomes large. Energy goes to infinity. Now, of course, we don't really mean infinite energy, again. But what we mean is that the things that have the same units as energy are very, very large compared, very small compared with the energy. So, in particular, what we mean here, what we actually mean here, is that h bar omega times n plus a half is very large compared with, something else that has energy, like, for example, 1/2 m omega squared average x squared divided by h bar omega. 0, excuse me. So, in other words, what we're thinking of is the large N limit. Okay? So in the large N limit, we expect the harmonic oscillator, the quantum harmonic oscillator, to exhibit classical behavior. Well, how can it do this? Because here's the potential energy curve. So this is V equals 1/2 k squared, or 1/2 m omega squared x squared, whichever you like. And in the quantum harmonic oscillator, what I'm trying to draw are equally spaced lines here, separated by h bar omega. Right? So the idea here is that in the classical limit, another way of saying this same thing would be that the spacing, h bar omega, is very, very, very tiny. Okay, why do we say that the spacing is tiny? Because remember, quantum mechanically, there are discrete energy levels. And the only way you could say that we're not doing quantum mechanics is if those energy levels are essentially all a continuum. Okay? Now, since the spacing doesn't become smaller and smaller and smaller as you go up, what you have to say is that you're in the limit that n is infinite. So that the total energy compared to the spacing is very, very tiny. So the total energy, h bar omega n plus a half, is very, 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 very small compared with the total to the, very, very large. Sorry, keep putting it the wrong way. Very, very large compared with the spacing, h bar omega. So in other words, n is huge. This makes sense, right? Sort of. Okay, so what does that look like in terms of the wave function? Well, as you know, the wave function for the ground state looks like this. The first excited state looks like this, and so on. And if you keep going up in n, the number of bumps goes up, right? So the number of bumps is actually equal to n plus 1. So this is n equals 0, this is n equals 1, and so on. So if you translate this to the probability density function, it looks like this. Probability density, that didn't come out very well. All right, there's a much better picture in the book, okay? So on page something or other, right, he has the, we're getting a little bit ahead of ourselves because this is, that's okay. Here it is, okay. So this is the picture I'm trying with absolutely zero success to reproduce. Here are the wave functions here, except they're going down instead of up the way I did it here. And here are the probability density functions. And you can see that this is just the square of the probability amplitude, of course. Notice that if you get to, if you just have 1 or 2, it's pretty, I mean, they're the same. But once you get to 3, look at this, the middle goes down a little bit. And 4 and 5 and 6, you can see that this effect becomes more and more and more pronounced. Why is this important? Because The classical probability density looks like this. Ugh. All right, there's an even better picture, even a better picture. My terrible picture there. All right, so this is what I'm trying to draw, okay? This guy here. But I don't want to draw it inside the curve, right? It goes like this because it goes like 1 over the square root, right? And you can sort of see here that the probability density function for larger and larger and larger n goes down further in the middle and it goes up further on the ends. Now why is that? What is the classical probability density function? Well, think of a pendulum, okay, as it swings, okay? Where is it most likely to be found? At the ends it's more likely to be found, just like this picture shows. Because why? Because that's the classical turning point. That's where it's moving the slowest. So in other words, it spends most of its time on the edges. Right? When it's in the middle, it's whipping by, all right? So it spends the least amount of its time there. So that's why the classical probability density function, it's really terrible because it looks like the x squared. But what I'm really trying to draw here is 1 over that square root function, which is equation 761. So this is p subclassical dx, and that's 1 over pi square root, oh, this is a dx, xn squared minus x squared. And it looks like that, okay? And you can derive it for yourself using the procedure at the bottom of page 259. I was thinking of putting that on as an extra credit problem, and I guess I will now that I've thought of it out loud. Because all you do is you say that the chance of finding a particle between x and x plus dx, which is p classical dx, is proportional to the time p classical dx is proportional to the time interval that it spends in that interval, all right? So that's dx over v, right? You can see that the units are right for that, right? So this is the time that it spends in that interval, right? And so you can derive this function exactly from that, and he sort of leads you through that. And I think I'll put that on as an extra credit problem if you'd like to do that. But all you have to do is just go through exactly what he does on bottom page 259, but I think it's kind of illuminating. Anyway, so if you wanted to find out what the what particular quantum value probability density function this guy is with all the bumps, all you have to do is count the bumps and then subtract 1, and that would be the n. What he's drawing here with the dashy line, that's n equals 10 to the 26th. And in other words, oh no, sorry, I'm sorry. No, the dashed line is a plot with classical probability density. So it actually is a plot of this. I'm sorry. I misread the book. Okay, so that's really all there is from number 6, and we're happy about that because it does have the right classical limit. Any thoughts or questions about that? Should we go on to section 7? Section 7 is time dependence, and here there's really, it's just the same principles that we know about the time dependence of wave functions that we found out in chapter 6 applied to our new system of harmonic oscillator. In other words, we know that if we know what the state of the system is at t equals to 0, then to find the state of the system at some other time, t greater than 0, all we have to do is act on this guy with the unitary operator u that we found out in chapter 6 could be written as, or earlier chapter I guess, but we found out how to do it in x space in chapter 6. Anyway, this u is e to the minus I Hamiltonian operator times t over h bar. And that comes about, as you'll remember from chapter 3, 4, comes about just from integrating the Schrödinger equation I h bar d psi dt equals h psi. So this is the time-dependent Schrödinger equation. And I mean, you can just integrate this doing just sort of the stupid calculus trick that we all learned way back when we were freshmen. Multiply both sides by dt and divide both sides by the ket, and then just integrate. Right? And as long as the Hamiltonian is constant in time, you get exactly this. So that's very cool. And in the time dependence section, then he talks about how we get how we get time dependence of different kinds of states. And specifically, he talks about the particular initial state psi of 0, which is a superposition of two adjacent energy states. I think he calls them Cn, n and n plus 1, does he? Yes, he does. So this is Cn on state n plus Cn plus 1 on state n plus 1. And it turns out, and it's not that hard to prove, that you can get a very nice equation for the time-dependent ket, and we're going to do that in problem 9. Okay, so he gives you a heads up about that. We're actually going to do problem 9 in class today. But right now, let's now go back to problem 7, which we were in the middle of, and finish it. Okay, so in problem 7, where are you, dear? There you are. Okay. Okay. It says that the right. Okay. So we found out how far did we get?
On 7?
Yeah, number 7.
You did get the average momentum.
I wrote down what the average momentum was.
Yeah.
And then I said that what the phase constant had to be, phi. Did I get that far?
I believe so.
Oh, okay. All right. Well, let me just summarize that. Okay. So what we're given is two pieces of information to begin with. That we're in two. So we've got a state psi. This is number 7. We've got a state psi which is a linear combination of the energy states 0 and 1, because they have energies h bar omega over 2 or 3h bar omega over 2. And I think I called those constants. They give us that the measurement of the energy, it has 1/2 probability of being this and 1/2 probability of being this. So I said, well, that immediately tells us what the amplitude is here. But we also have a possible phase difference between the two states, and I called that phase difference phi. So in order completely to characterize the state, we needed at least one more piece of information. And the other piece of information that he gives us is that the average momentum at time t equals 0 was m omega h bar over 2. So that can't be right. It's got the wrong units. Oh, square root of that. Okay. All right. So those are the two pieces of information we got. And so so we proceeded to evaluate this with this unknown phase in there, hoping that we'd get an equation that we could use to find out what the phase was. And all we had to do was put in for p that this was minus I square root m omega h bar over 2 a minus a dagger. And what we got was minus I square root m omega h bar over 2. Oh, excuse me. Sine phi. Oh, I remember this. I forgot the minus sign, and so I got the wrong answer. I remember this. Yeah. But then I found out that this is great. Okay, so we know that. Okay, so what does that tell us? That tells us that we can actually find out what phi is here, because this has to equal this. In other words, this has to equal 1, because this has to equal this. So therefore we have that sine of phi equals 1, which means that phi is pi over 2. And so we can just immediately write that in here. Okay, so that was the first part of the problem. The second part, or the last part of the problem, was what is the average of the momentum at time t? Okay, so we know what the thing starts out at. This is at time t equals 0. So immediately we know that psi of t, just like it says over there, is e to the minus I ht over h bar psi of 0. And very cleverly, we've written the state in terms of energy eigenstates, so we know exactly how the exponential of the Hamiltonian operates on them. In other words, if we have the exponential e to the minus I ht over h bar operating on any energy state, eigenstate n, well, this just gives us e to the minus I en t over h bar. And back again, because if it's an energy eigenstate, then it's also an eigenstate of any function of the Hamiltonian, as well as of the Hamiltonian itself. Okay, so that means that we can just find out what this is very easily. Just plug that in, and we get 1 over square root of 2, 0, plus, you know what, I'm just going to say what e to the I pi over 2 is. It's I, right? So this is plus I over square root of 2, 1. Okay, so this is 1 over square root of 2 times e to the minus it over h bar times h bar omega over 2, because I just plug in what the energy is for the ground state. So the h bar goes away, and this is I times e to the minus I t over h bar 3 halves h bar omega. So the h bar again goes over there. Okay, so that's psi of t, and now to find the average of p at time t, all we have to do is put in psi of t. Which is minus I square root m omega h bar over 2. Let me take out my 1 over square root of 2. And another 1 over square root of 2 from the other side, right? And if I put the bra on here, that will be, nobody stopped me. My state's disappeared. All right, now I'm going to put the bra. Okay, so that's going to be 0. And e to the plus it omega over 2. Well, I omega t, I guess that's another way of writing it. And then minus I e to the plus 3 halves I omega t. And we have the bra 1. And then we have a minus a dagger. And then we have the cat. And I've already taken out the square root of 2 from both sides, so I'm not going to have to do it again. E to the minus I omega t over 2, 0, plus I e to the minus I, 3 halves omega t, 1. question about that? Is this okay? Okay, now these guys, now that I've evaluated them, they're just numbers. But there are different numbers multiplying the 0 state and the 1 state, so I had to carry them along. Okay, but they're not operators; they're just numbers, and I just have to, make sure I don't, screw them up or whatever. When A operates on 0, remember A is the lowering operator, so this just gives you 0. Yeah. But when A dagger operates on 0, this gives you square root of 0 plus 1, which is of course 1, times the 1 state. Okay, when A operates on 1, we're going to get the 0 state times square root of 1, but I don't care about that. So this is the 0 state. When A dagger operates on 1, we're going to get the 2 state times square root of 2, but this one is also going to give us no contribution. Okay, this one clearly gives us no contribution because it's just 0. But this one also gives us no contribution because when I then multiply this bracket by this bracket, there's no 2 state over here. Okay, so the overlap is going to be 0. So this thing doesn't give us any contribution, and this thing doesn't give us any contribution. But the A dagger operating on this does, and the A operating on this does. So I only have 2 terms here. So I'm just going to write them down. So starting from here, this is e to the minus I omega t over 2. And the only thing that comes from the 0 state is the A dagger. So that's going to be a minus, and then the 1. Now the only thing that comes from this guy, let's put down the thing. So this is I e to the minus I, 3 halves omega t. And the only thing that comes from this guy is where the A operates on it. So that just gives me the 0. So there it is right there. Still okay? All right. Now, instead of this times this giving me 4 terms, it only gives me 2. Why does it only give me 2? Yeah, because the 0 has no overlap with the 1 state, and the 1 state has no overlap with the 0 state. So I only get something with the same, with like terms. And in which case, as long as the normalization is taken care of, everything comes out in the wash. So this is minus I square root m omega h bar over 2, 1/2, and 2 terms. The 0 times the 0 state, so that's going to give me e to the plus I omega t over 2 times I times e to the minus 3 halves I omega t. And then I get a term from the 1 state, which is minus I times minus is a plus I. So then we've got e to the plus 3 halves I omega t, and then e to the minus I omega t over 2. And that's all I get. Minus I, sorry. Okay, now notice that minus I times I, of course, gives you 1. So this thing cancels this and this. Which is nice, because I don't want an average value of the momentum to be imaginary. That would make me upset. Yeah, right. Okay, and also notice that this term and this term are the complex conjugates of each other. Again, we're happy, because any number times its complex conjugate, any number plus its complex conjugate just gives you twice the real part. Okay. Again, that makes me happy, since now everybody is real, for sure. Okay, so what do we get here? We get, since this is a plus, I should break down what this is. The plus I omega t over 2 and the minus 3 halves I omega t, this gives me 3 halves minus 1/2 is 1. So this is e to the minus I omega t. And this is e to the plus I omega t. So this plus this gives me twice the cosine of omega t. So the 2 here cancels the 2 here. And the answer is, finally, that the average of p of t is square root m omega h bar over 2, which is nice because that gives us the units of momentum, times the cosine of omega t. So it's a perfectly reasonable answer. And you can see that at t equals to 0, the cosine just becomes 1, and you get square root m omega h bar over 2, which is, of course, what we were told was the correct answer. So this agrees with my arithmetic on my paper, so I'm happy. Everybody good? Okay. Okay, what we're now going to do is number 9, and you remember, oh, I forgot to write this down here. The book claims that for, this one's not good. Go to the unoccupied table. The book claims in section 7 that if you have any state that's of this form, where it's a linear combination of any energy state plus its adjacent energy state, that you get a lovely value for the average of x, that it's just equal to a constant times cosine of omega t plus phi. You might have oh, excuse me, delta. Use delta. So there's a possible phase offset there, but it just looks like a cosine. Okay. Now, why is this kind of a nice expression? Well, it's a nice expression because this is exactly what you'd expect from a classical harmonic oscillator, right? The average of the x, or in fact, here we have an average, but you don't need an average classically, right? You can just write down the solution to the equations of motion for a harmonic oscillator. You just get x equals, amplitude times cosine omega t plus phi, right? Or, excuse me, delta. Okay, so he claims that this is true, and in problem 9, we actually show this. So that's what I'm going to do for you is problem 9 right now. So, I think I have that correctly phrased. Oh, yeah. All right. So, okay, he wants you not only to show this, but also to show this, that the average p is minus m omega a sine omega t plus delta. So both of these are very familiar expressions that would correspond to a classical harmonic oscillator. So let's see how that works. Okay. Okay. So it gives you a little tip-off. He says Ehrenfest's theorem is 633 and 634, and so I'm just going to write down what that is. 633 is down on my paper, but I guess I didn't. Ah, okay. So here's Ehrenfest. So this is on page 199 of your book. So Ehrenfest says, and again, we recognize that these things are what we're very used to for the for classical mechanics. If you just get rid of the pointy brackets, I mean, classically, we would just have dx dt equals p over m, or if you like, v, right? And we'd have dp dt equals the force, which is minus the derivative of the potential energy with respect to x. So this is classic. This is Ehrenfest. And we want to show that if we happen to have an initial condition for the state of the harmonic oscillator that looks like this, that we will get this, which are solutions to this for the harmonic oscillator. Okay. So these are the solutions to the Ehrenfest equations for the particular potential energy that we happen to have. In other words, V for the harmonic oscillator is 1/2 m omega squared x squared, so minus dV dx is obviously m omega squared x with a minus sign. and in fact that does correspond right there. But I mean, that's what you would get. So let's see how this particular form of initial condition can lead to that. So this is problem 9, and we're not only showing this but also this. All right. So let's actually find out what the time-dependent state is if we have this. So if we have psi of t, right, this would be e to the minus I ht over h bar psi of 0. But we know this, so we can write that this is Cn e to the minus I t over h bar times h bar omega n plus 1/2. And that's times the n state plus Cn plus 1 e to the minus I t over h bar omega n plus 1 plus 1/2, or n plus 3/2 if you like, n plus 1. So that's psi of t, and it's just very, very straightforward. I'm going to rewrite that, as in fact your book does, in equation 763 as, let me get this notation right here, e to the minus I, I can't read my writing. I said it was equation 763, so let's just go look at it. Here it is! Great! All right. E to the minus I, n plus 1/2, h bar, excuse me, omega t, times Cn n plus Cn plus 1 e to the minus I omega t n plus 1. In other words, he's taking out the constant term. That's this term, because this term has that term in it also, but just has one more factor of minus I omega t. Okay. Now, if we want to know the average value of x, so that we can show this, all I have to do is bracket it in, put it in between the bra and the ket, just like this. And then I'm going to put in what the operator x is in terms of the raising and lowering operators. And so that's, this guy is square root h bar over 2m omega a plus a dagger. Okay, and again we're going to get let me just put in the bra and the ket. So this is, let me not screw this up. Cn star n plus Cn plus 1 star e to the plus I omega t n plus 1 Then we have this stuff, h bar over 2m omega, and a plus a dagger. Sorry, I need this room. And then we have Cn n plus Cn plus 1 e to the minus I omega t n plus 1. Okay, now you'll notice that this term completely went away. How come?
Because it's complex.
Because, right, exactly, because there's an e to the plus I garbage from the bra and e to the minus I garbage from the ket, and I just canceled it out. So that's not terribly mysterious at all, actually. Oh dear, I want to keep this. You know what? I'm going to have to go over to the next board. Okay. So, again, what we're going to do is see what happens when these guys operate on these. When A operates on N, what do I get? It's the lowering operator, so I'm going to get square root of N times N minus 1. In case you didn't know. And when A dagger operates on this, what do I get?
Square root of n plus 1.
I get square root of n plus 1 times the state n plus 1. Okay, and similarly over here, when A operates on n plus 1, I get square root n plus 1 times n, and when A dagger operates on n plus 1, I get square root n plus 1, n. A dagger. Wait! Ah! A n. N plus 1. A n plus 2. Thank you! I should actually look at my paper instead of looking at all that in my head. Okay, so which terms are we going to have non-zero overlap with this guy with? That didn't come out. Okay, the only things that are going to have non-zero overlap are where we get a ket that's n or a ket that's n plus 1. Right? The other guys aren't gonna matter. So this guy will have no overlap, and this guy will have no overlap. So I don't care about that. So this whole thing then is square root h bar over 2m omega. All right, so I'm going to do the n overlap, and the only one that I get from the n is this one. So that came from this guy here. So that's going to give me a Cn plus 1 and a Cn. Have I done that right? Maybe. Cn star, Cn plus 1. And then we have an e to the minus I omega t. And of course we have an n. Oh, and we have a square root n plus 1, sorry. I think that's it. Yep, I'm good. Everybody agree, I hope? All right. So that's this. We also have this. So that's Cn plus 1 with a star, right? And then e to the plus I omega t, right? And then square root n plus 1 from this guy, and n plus 1, yeah, that's it. Let me just check my notes here, see if I hadn't screwed that up. Nope, I didn't. Amazing. Okay. Notice how the n plus 1 is common to everybody. And, in fact, how this term here is the complex conjugate of this term here. Or it would be if I'd written down C n plus 1 and Cn. There we are. I said that was correct, and then I screwed it up. Anyway, the first term is the complex conjugate of the second term. So that makes us happy, because why? Because now the average of x is actually going to be a real number. So that makes us delighted, okay? But what we're going to call it is a over 2. So we're going to say that let square root h bar over 2m omega times the real part of this, in other words, Cn star Cn plus 1 square root n plus 1. Let that real part of this. Well, actually, you know what? You can just put this, and then we'll put Cn star Cn plus 1 plus Cn plus 1 star Cn. There we are. All right, so we're going to set all this stuff equal to a over 2, so as to correspond with this. And then the e to the plus I omega t and e to the minus I omega t is just going to become twice the cosine. So no, I screwed that up. Ah! All right. Yeah, of course I screwed it up. So let a over 2 e to the I delta equal square root h bar over 2m omega Cn star n plus 1 star Cn square root n plus 1. Ah, there we go. This will work. Then the average of x is equal 1/2 a, that's the a over 2, e to the I omega t, e to the I delta, plus 1/2 a, e to the minus I omega t, e to the minus I delta. And so this is just a cosine omega t plus delta. Woo! Got all tangled up there in my constants, but finally we did get this. So, woo woo. All right, we can do something exactly similar for p. Okay, so let's do that. So the average of p is going to equal psi of t p psi of t, which is, just as we had here, Cn star n plus Cn plus 1 star e to the I omega t n plus 1. And now we can put in the p operator, which is minus I square root m omega h bar over 2, a minus a dagger. And then we put this part here. So that's Cn n plus Cn plus 1 e to the minus I omega t n plus 1. Okay, so this, again, we can do these operations here, and again, sorry, right. So again, we can do the operations, and again, this term and this term are not going to give us non-zero overlap over here. So again, we can combine the terms, this guy with this guy, one of the things with this guy, and this guy with this guy. So just as with the x, except we've got a minus sign to keep track of now. And let's hope that I've done it right here on my paper. So, all right, this will be minus I square root m omega h bar over 2 Cn star Cn plus 1 square root n plus 1 e to the minus I omega t minus Cn plus 1 star Cn square root n plus 1 e to the plus I omega t. So it looks very similar to this, except a different constant out in front and a minus sign in the middle. And that just comes because we have a different constant because it's momentum, and because this is a minus a dagger here. And so using the exact same definition for my a there, I get that this is m omega times a over 2I times e to the minus I delta e to the minus I omega t minus e to the I delta e to the I omega t. And this, of course, here is 2I times the sine of omega t minus 2I. Yeah, no, plus. No, minus. Minus. Right, because the minus is over here and not over here. So again, we recovered this. So, woot woot. Sorry that was so long. But anyway. Any questions about that? So that's number 9. Everybody good? Number 9. Okay. Now the next prob that I'm having to assign you for homework is number 11, and number 11 is actually on section 10. So I'm going to skip that, even though it's a pretty easy problem, until we actually get to section 10. Number 13, weirdly, is on section 6, which we've already gone over. So I'm going to do that one now, if everybody's okay with 9. We will come back and do 11, but 11 is about the parity operator, and we don't talk about that until section 10 of this chapter. So I don't know why I did this.